This is John from PrepWorks, and I'm going to be going over everything you need to know for Unit 1, which is the largest unit of AP Calculus A, B, and BC. This section discusses limits and continuity, both of which are key to understanding later units. On the AP exam, MCQs will be about 10 to 12% limits for the AB and 4 to 7% of those of you who are in BC. Now, we're going to go over these 16 topics in pretty deep detail, but if you want a full study guide that's 100% free of charge, make sure to check out the link in our description and in the pinned comment for more. Now, let's get started. Remember that each of these topics is modeled on the College Board's course and exam description. Topic 1.1 introduces calculus, and it introduces the concept of a limit, which is what we'll continue to explore throughout this unit. Calculus is the study of change. It models dynamic change using a tool known as the limit, and we're going to get into that, but first we need to present some simple concepts. So, you may recall from algebra that to find the value, the y value of any function at a given point x, say this one, we could simply plug in the x value and then we would get a y value. So if we wanted to find what y was equal to when x is equal to 5, we would simply do y equals 5 squared, which is 25. We could also just look at a graph and see that it was in fact 25. But in calculus, the limit changes that. We do not want to find what the value is at 5. We want to find what the value is infinitely close to 5. So, for example, the limit as we approach x equals 4 for this function is equal to 16. Okay. How do I know that? How do I know that? Well, as we see from this table, as we get closer and closer to the x value 4, which would go right here, we get closer and closer to the value 16. We go from 15.2 to 15.9. We go from 16.8 to 16.08. Right? We're getting closer and closer to this value 16. And if we continue to extend this table to something like 3.99999999999, and infinitely kept going, we would get closer and closer to the value of 16. Okay? But it does not matter for calculus what that value truly is if we're trying to find the limit. Okay? Now, the other thing the College Board wants you to know for this topic is that the average rate of change is undefined when the change in the independent variable is 0 and the change in the dependent variable is non-zero. So essentially, that's a straight line. Here, there is an undefined rate of change. With a vertical line, there is an undefined rate of change. And that's all you need to know for topic 1.1. Topic 1.2 discusses defining limits and using limit notation. Topic 1.2 is very simple. It shows this common notation that all limits have. Let's break this down. This is the limit operator. It's simply LIM. Usually we use a cursive L to indicate that it's not a 1. Then we have a function here. This is the function that we are finding the limit of at a point. And that point is c. So if I wanted to find the limit of a function, let's say f of x equals x cubed, it would be written as a limit of x cubed as x approaches. Let's say I wanted to find the limit at x equals 4. This would be equal to some real number, hence r. We're going to get into how you would find that limit in future topics. Another thing to note is that the epsilon delta definition is specifically not assessed by the College Board. If you learn this in your Calculus AB or Calculus BC class, you can ignore it for the purposes of the AP exam. However, on a unit test, it might be assessed if your teacher taught it in class. Topic 1.3, estimating limit values from graphs, is one of the biggest topics in all of AP Calculus AB or BC. There's a lot to break down here, so let's get into our first bit here. We've got one-sided limits. One-sided limits evaluate a limit as we approach only from one direction. Previously, we introduced the limit as something like this, where we have a function and we want to evaluate from both sides, right? We evaluate from both sides at some point. Let's call this c. Okay, and our value here, whatever value that we get as we get closer and closer, is the limit at c, right? And we wrote that as lim x approach c of f of x is equal to r, or equal to L, or some real number, right? The one-sided limit is different. It only evaluates from one direction. This is especially helpful for when we have a piecewise function, or something where when we approach a value c, we get a different direction if we approach from the right than from the left. And that full limit that we discussed earlier, that LIM as x approaches c, that only exists if the one-sided limits are equal. Now let's take a look at this graph here. As we approach from the left, we see we get some value, let's call this a. But as we approach from the right, we get a value b at the same point c as we get infinitely close to c. Now notice I have a little circle here, and I can make that a little bit more clear here. I have a little circle right here. Okay, that means that the function is not defined at that point, but it is defined at every point as we get infinitely closer from this direction, right? And we don't care about what c is actually equal to, because remember, in a limit, we want to know what the value is as we get infinitely close, not the value actually at that point. Okay. Now we see here we're coming from both directions. We're getting different answers. These are one-sided limits. This is our one-sided limit from the left. This is our one-sided limit from the right. And how do we notate that? Well, of course, we have another rule. So as we evaluate from the left, we add a little minus sign right after the c. And as we evaluate from the right, we add a little plus sign. I like to remember this as a pair of axes. If we have an x-axis, then this is the negative side and this is the positive side. And that makes sense because this is on the left and this is on the right. It's the same way for this. Okay, let's take a look at an example here. If we're trying to find, this is the right side, remember, because we have a plus. If we're approaching from the right side, what do we get? Well, as we approach 0 from the right side, we get -6. Our limit is equal to -6. As we approach from the left side, we get the same thing, also -6. So what can we say about this function at x approaches 0? Right, the limit as x approaches 0 here is clearly -6 because it is the same from both the right and the left. So we can say that the limit as x approaches 0 with no plus or minus after it of f of x is equal to -6 because these are the same. That's another rule. The limit only exists, the full limit, right, only exists at c when the one-sided limits are equal. So in this case, the one-sided limit at c does not exist, right? It does not exist because this way, this one-sided limit is not equal to this one-sided limit. Now we can use graphs as we just did, but we do have to be cautious. It's possible, for example, that if I did not know that this function was f of x equals 4x minus 6, right, that there could be some sort of complicated algebra here and there was a little jump right here. And I wouldn't know because my graph window is different. So caution must always be used when we're using a graph. Now, let's also take another look at something that's a little bit different that we can see from a graph. A limit fails to exist when we have a jump discontinuity, a vertical asymptote, or a domain with oscillating behavior where the period of oscillation approaches infinity. Oscillating behavior is also observed in something like, sine of x, and we can see if we try to find the limit at whatever this point is here, we would be able to find that limit, right? Now, let's take a look at that. We're going to get more into depth with that in a second, but first, let's take a look at a vertical asymptote here. We can clearly see we have a vertical asymptote at x approaches 0 from both sides, right? This side doesn't exist, dne is what we write when it doesn't exist, and this side doesn't exist, right? When we approach from the right, it approaches a asymptote. We approach from the left, it also approaches an asymptote. So that doesn't exist, and the full limit doesn't exist either. Also, dne. Let's take a look at that oscillating behavior I mentioned earlier. This is not even oscillating behavior. This, as we approach 0, the oscillating behavior, the period of that oscillating behavior approaches infinity, unlike something normal like sine of x, where it's pretty constant, right? It is constant, right? From here, we see that we can't really figure out where it's going right here, right? It's anywhere between 1 and -1. It could be anything, right? So this doesn't exist either, right? And this also doesn't exist. From both sides, whichever way we approach this function as we get to 0, we can't tell what this limit is, right? Take a look at another example right here. Okay. This is very hard to see, right? You might think that both of these approach 0, right? You might think that this approaches 0 from this side, approaches 0 from this side. But when we zoom in, we see this is not the case, and this shows another pitfall of using a graph, right? We have an expanded window where the scale on our x-axis here is 50, or on our y-axis is 50. It's huge, right? But when we change that scale to 0.5, we can see that as we approach from the right direction, we get 1. And as we approach from the negative direction, we get -1. When we approach from the left, we get -1. When we approach from the right, we get +1. Therefore, we can also say for this one that the limit of the full function as x approaches 0, dne, right, for f of x here, does not exist, right? Because when we approach 0 from different sides, the one-sided limits are not equal. 1 is not equal to -1. So there is no limit that exists here. Topic 1.4, estimating limit values from tables. Now, if we're given a question where we simply are given a function, let's say like x cubed, the best way to solve this is through algebraic manipulation, discussed in topics 1.5 and 1.6, or by using a graph, discussed in topic 1.3. But let's say, given this table here, and we were not given this function, right? How would you go about solving this on a no calculator portion of the AP, right? You won't be able to draw a graph because you don't know what the function is. The function, as you could see it, is only defined by these 4 values. How would you find the limit using only a table? Take a second and think about it. Can you find the limit as this one approaches 4? Can you find the limit of this graph as x approaches -5? Okay, let's take a look at this. So we see here that from both directions, as x increases or decreases, as it increases from this direction, decreases from this direction, as it gets infinitely closer to x is equal to 4, we are getting closer and closer to 5. Therefore, this one is simply 5. But this one's a little bit more complicated, right? From this direction, it's coming and it's -1, and from this direction, it's +1, right? What's the difference? Well, here, even as we change x, y is not changing from this direction, and neither is it changing from this direction. We can see, if we were to take a one-sided limit, that the limit, as we approach from c negative, right, is equal to -1. And the limit, as we approach from the right, is equal to +1. And because the one-sided limits are not equal, that means the limit does not exist. So the limit of this function as we approach 5 is dne, does not exist. And how can we tell it from the table? Well, as we change x from this direction, change x from this direction, this one is staying at 1. It's going to continue being 1 as we approach 5. This one's going to continue being a -1 as we approach 5 as well. Topic 1.5, determining limits using algebraic properties of limits. This is a fairly simple topic, but it's certainly an important one. And though we're going to get more into determining limits using algebraic manipulation in topic 1.6, this is important for just knowing some properties that you can use to help solve those limit problems in the future. The first one we have is constant multiple. So when we have a multiple, let's say 3, and we multiply it by a function f of x, let's say x squared, then what we can transform this into using limit properties is 3 of limit x squared. And I'm not putting the x arrow c. You should, but this is shorthand. So for the sum and the difference, these are both the same, just a difference between a plus and a minus. But of course, when you add a negative number, it's the same thing as subtracting. When we have the limit of two functions added together, let's say x squared plus x to the 4, we can split that into x squared and then x to the 4th, right? We can split those up. Same thing goes for difference. And for a product, it's the same idea, and same thing with a quotient. When we have two functions that are related to each other by one of these operators, plus, minus, divide, and multiply, we have two functions that are related like that, we can just split them apart into their own limits and evaluate them separately. Now, for the power, it's a little bit different. If we have our power rule here, right, this is raised to a power, we can just evaluate the limit first and then raise it to that power. Same thing with a root, because of course, root and a rational exponent, it's the same idea, right? We can evaluate the limit and then the limit of the function like this, or we can just take the nth root after we take the limit of the function. Okay, topic 1.6, determining limits using algebraic manipulation. This is by far the easiest way to solve a limit if it's possible. Now, you can only really do this if you're given an equation. If you're only given a graph or a table and asked to find the limit of a point there, you cannot do that. You cannot do that using this method. But if you're given a function, right, there are several different ways to solve, and it depends on the function family that you're given. Let's say I have a polynomial function, something like x to the 4th plus x to the 3rd plus x to the 2nd plus x to the 1st, right? We're trying to find the limit of this function as x approaches 4, right? What is this equal to? Well, as we see here, our rule is that we just simply plug in c, and this is our c value, right? So we would get 4 to the 4th plus 4 to the 3rd plus 4 to the 2nd plus 4. And that is equal to our answer. On the AP, you do not need to simplify. You do not need to simplify this answer. You can just leave it like this. Okay? Do not try to simplify because you might make a mistake and it'll also cost you time. You have limited time on that exam. It's best not to waste it. Now, rational functions. First thing you should do is always remember to factor the numerator and the denominator, right? Let's say we had the limit as x approaches 2 of x plus 2 times x minus 2 over x minus 2. If we were to plug 2 in here immediately, we would get 0, right? We get 2 minus 2 in the denominator, we just get 0, right? So what we need to do is we need to factor this out. All right, these two cancel, this cancels here, and we get the limit as x approaches 2 of x plus 2. Now we're in polynomial form. So we can just plug this in and we get 4. All right. Now, radical functions are a little bit different. There's something special you have to do here that you might remember from Algebra 2. If not, be sure to check out that video. But we need to rationalize the denominator. So if we have a function that's in the form like this, right, a over b minus square root c, we have to multiply by the conjugate, which is like the reverse sign, right, times the top and the bottom. And then we would get a form that looks like this, right? We get a times b plus square root c over b squared, right, minus c. So you have to rationalize that denominator. Then once you do that, you just plug in whatever c value you get, unless the nth root is positive and the radicand would be negative, because let's say if we took the square root of something like -2, this is going to result in a complex number, which is not what we want. The AP likely will not give you anything complicated like that. Now, for a composite function, let's say I have the function f of g of x, right? The limit here, x approaches c. What you want to do is you find the limit of the inner function. So use one of these above strategies or any other strategy to find the limit of the inside function. So you plug in c whatever. You find the limit of g of x. Just treat it as lim, all right, like this. Then to find the outside function, you're going to get some value. This is going to be r, right? What you want to find then is you have the limit as x approaches r of the outside function. And that's how you'd find that value. Remember, you're not doing c in the outside function, you're doing r. And that is topic 1.6. Okay, so here we've combined topics 1.7 and 1.9 because they're both essentially practice topics. What the College Board says in their course and exam description, that there's no new content for these topics, just a practice question. So, evaluate this limit here. I'll give you a couple seconds to do it. Alright, now I'm going to get rid of these answer boxes here. We're going to go over it. Okay, so the first thing is we're going to use our algebraic manipulation strategies from topic 1.5. So we can bring out this constant multiple and put it here, right? We bring out the constant multiple. The next thing we can do is factor out an x from the top, right? We're just factoring out an x up here. Then these x's cancel and we're left with this, right? Now we're left with a rational function. There is no way to divide this rational function up, right? We cannot factor out anything here. So we're left with this. We're going to plug in our c values, right? We're plugging in our c value here, and we're left with this number here, right? We're left with this number here, 5 times 6 over 48, which equals to 30 over 48, which is equal to 0.625. Now, you may be thinking, you could factor out a 3 here, right? You could factor out a 3. Yes, you could, but it doesn't really matter at this point, right? You can just put it in immediately. To take out a constant multiple is really only to help you. And here's what I'm thinking, right? When I solve this, I see that if I have 3 times 9x minus 2, then my constant multiple becomes, right, it would become 5 over 3, which is harder for me to multiply than if I just keep it, right? It's harder for me to multiply that. So I'm just going to leave it. Topic 1.8, determining limits using the squeeze theorem. So the squeeze theorem can be used to evaluate the limit of a function if we have this function that's bounded by 2 other functions. So if we're trying to find the limit of a function at a point and we need 2 other functions, that means we need 3 total. And the first function, right, has to be less than or equal to the function we actually need, right? This is the function we need. This is the function we're trying to find the limit of, right? And this function must be greater than it. over the interval surrounding but not necessarily including the point x equals c. So if we had, let's say, a function here and this is all true, but then like there's a random thing that's defined up here for that function, it doesn't matter, because if this is c, right, we're only looking at the interval surrounding c, not necessarily at c, right? If this is true, under these conditions, if the limit of the bottom function at a point is equal to the limit of the top function at a point, they're equal to the same thing, right? Then the limit of the middle function is equal to that same point. I'm going to take a look at an example here, okay? We have a top function, right? We have a bottom function here. We have a top function, we have a bottom function, okay? This is always in between these two functions for the interval surrounding c. Let's call c 0. This one is equal to 0, right? The limit as we approach 0 of this function is 0. Same thing for this one. By the squeeze theorem, therefore, we can say that this limit is also equal to 0. Okay? Now, you'll notice why we have to use the squeeze theorem. It's because when we have something like this, the real image of this, right, if we zoom in, we get something like this, and this is a little bit more complicated to evaluate. So we can just use the squeeze theorem. We can see that this is, in fact, actually 0. Okay? Now, here's an algebraic example. This is very interesting. If we have two functions and we know like the value of those functions, we know the limit value of these functions, right? Let's say we have something like the limit of tan x over x, right? Tangent x over x, right? If we know that we can make this look like functions that we already know the limit of, then we can use this idea to kind of transfer our knowledge. So let's say if that seems abstract to you, let's take a look at an example here. So tangent x over x, this is equal to, we have tan of x is equal to sine x over cos x, right? So we're gonna put into this equivalent form, and we're gonna kind of algebraically manipulate it a little bit, and then we can use the squeeze theorem. Okay, so this value here, right, as x approaches 0, and this value here as x approaches 0, they're both going to be equal to 1. Okay? Therefore, because both of these are equal to 1, and we can just multiply equal to 1, right? But we can also use the squeeze theorem. If this top function, this bottom function are both equal to 1, then this one also must be equal to 1 by the squeeze theorem. But what we also saw here, right, is through algebraic manipulation, as we saw earlier, if we split this up into two different limits, evaluate them separately, we still get 1. But the squeeze theorem kind of proved this, because if you were to graph all this out, right, then you would get a bottom function, a middle function, and a top function. And those would be equal to 1 at the same point. The next topic of discussion in the unit of limits and continuity is, of course, continuity. But to explore continuity, we also need to explore discontinuity. Discontinuity occurs at vertical asymptotes, jump discontinuities, oscillating behavior, and removable discontinuities. We're going to get into that last one in a little bit, but first we're going to go over those first three. So, a vertical asymptote is right here, and notice these are essentially the same as when a limit doesn't exist, right? We see here there is clearly a discontinuity here, vertical asymptote example. Okay, let's take a look at oscillating behavior. We see oscillating behavior, also a discontinuity. The last one here is jump discontinuities. It's a little bit new. Basically, when we have a function that makes a jump, essentially right here we have a jump, right? That's called a jump discontinuity, and it is a type of discontinuity. This is basically only seen in a function that has either absolute value x over x, something like that, or a piecewise function. All right, topic 111, defining continuity at a point. We previously discussed discontinuities, but it's always good to have a rigorous definition of what continuity is. And there are multiple different types of discontinuities that we should always be aware of. Okay, so a function is continuous at x equals c if and only if, firstly, the function exists at that point. Secondly, the limit exists, meaning that the two-sided limits are equal, right? This limit here is equal to this limit here, right? If those two limits are equal, and if these two things are equal to each other, right? So, we have another rule. If the function g is continuous at c, and if the function f is continuous at g of c, then the composition f of g is continuous at c. Given these rules, let's take a look at an example question. Given g of x below, is g of x continuous at x is equal to 2? Take a second and see if you can solve that. Okay, I'm going to get rid of the square here, and we're going to take a look at the answer. So, firstly, we need to evaluate both sides of the limit, okay? Now, we know that if we have this here, then we're going to have something only at 2, and then we're going to have something that's going to be the same type of function on either side of 2, right? Well, we can split this into, right here, we can split this into a limit here. So limit as we approach 2, remember it's everywhere but 2, so we know that it approach 2's from both sides. We can expand it to be like this, we just cancel out the x minus 2's and we get 4. Okay, but the real g of 2 is 3. So we found that this exists, right? This exists, this is equal to 3. We found that this exists because the two-sided limits are equal and it's 4, right? But 3 is not equal to 4. So g of x is not continuous at x equals 2. Even though the limit exists, it is not continuous. Okay, topic 1.12, confirming continuity over an interval. So in topic 1.11, we confirm continuity at a point. Unsurprisingly, for a function to be continuous over an interval, it just means that the definition for continuity at a point is satisfied for the entire interval. Now, to be continuous on the closed interval AB, a function has to be continuous, but the left one-sided limit must also be equal to f of a, and the right-sided limit must also be equal to f of b. Essentially, this is just a definition of a closed function. We're including the endpoints. There are several types of functions that are always continuous over their entire domains. Polynomials, power functions, exponential functions, absolute value functions, rational functions, logarithmic functions, and trigonometric functions. Okay, that was a lot. Now we also have a similar rule to 1.11, right? If the function g is continuous over an interval and the function f is continuous over the same interval, then the composition of the two is also continuous over that interval. Now, given all of this information, let's try an example question. Take a second and see if you can solve this. Okay, we're going to get rid of our box here. Given f of x is equal to 3 to the power of 2x minus 1, show that f of x is continuous over the domain negative infinity, positive infinity, by so basically every real number, by expressing it as a composition. Well, we have a composition here. G of x of h of x is how we're going to call it. And our h of x is 2x minus 1, and our g of x is 3 to the power of x. This is an exponential function. This is a linear function, right? We know from this list up here that those are always continuous. Therefore, this function is also always continuous. Topic 1.13 is pretty self-explanatory, removing discontinuities. For a removable discontinuity to exist at a point C, that means that the limit exists. So the two-sided limit, right, basically exists. So we're approaching, let's say we have C here, we're approaching it from the same side, we're approaching the same point. But at this actual point, it's defined somewhere else, like let's say here. And we could remove this discontinuity by making the function defined where it should be, right, where the limit tells us, right, where the limit is equal to at that point. Let's take a look at a 2012 AP Calculus AB release exam question. This is multiple choice question number 9. Take a second and see if you can solve it. Okay, let's get rid of our box here. Let f be the function defined above, the piecewise function. For what value of k is f going to be continuous at x equals 2? All right, so we have this function, right? We're going to try to find the limit of both of these right here. First thing I notice is that we can just cross this out. These are going to factor, right? And we're going to get 2x plus 1. So the limit here, as we approach 2, as we plug in, right? We have a linear function, so we just plug in c now. Is going to be equal to 5. And so that means that the limit, right? The limit of f of x as we approach 2 is equal to 5. For it to be continuous, this needs to be equal to, right? It needs to be equal to it, right? So that means that f of 2 must be equal to 5. So k must be equal to 5. Our answer is E. This is our third to last topic, topic 1.14, connecting infinite limits and vertical asymptotes. So what is an infinite limit? An infinite limit is when at any given point c, f of x can be described to be equal to positive or negative infinity. Now, the limit still does not exist here. Some calculus books are a little bit wary on this, on whether it does or does not exist. Generally, it is accepted that this limit does not exist because for a limit to be defined, it usually has to equal a real number. So let's say at 0, right? What's the limit of this function as x approaches 0? Well, we come from this side, and it looks like it could be infinity. When we come from the other side, it looks like it could be negative infinity, right? This shows, right, an infinite limit. This is an infinite one-sided limit, another infinite one-sided limit, right? Where when we approach this point, we're going towards either negative or positive infinity. In this example, some calculus textbooks might assert that the limit as x approaches 0 of this function is equal to infinity, because no matter which side we go from, we are approaching infinity as we approach 0. But for the purposes of the AP Calculus courses, we're going to say that this limit does not exist because we're at a vertical asymptote. However, it is a good idea for you to know what an infinite limit is. And again, it's very simple. At an infinite limit, it just means that the graph seems like it's going towards either positive or negative infinity. Topic 1.15, our second to last topic, connecting limits at infinity and horizontal asymptotes. So in topic 1.14, we discussed what an infinite limit is. This is a limit at infinity. So what does that mean? Well, you can see here, it's simply written as x instead of c, we have a positive or a negative infinity. It's not this. It's not this. Okay? This is here for a limit at infinity. Now, the limit of a function at infinity can be approximated by simply plugging in infinity. Okay? So if we had like a polynomial, we plugged in infinity for x in that polynomial, we would clearly see, right, that polynomial is either going to grow towards either positive or negative infinity depending on the degree, or depending on the leading coefficient's degree, right? Now, the behavior, right, the behavior of this function is represented by positive or negative infinity if there's unbounded positive or negative behavior. But again, this limit doesn't exist because infinity is not an integer. So whenever you get that limit, right, whenever you evaluate something like this and it is not equal to a number, the limit technically does not exist. There's a special thing here. If we have a limit of a rational function, it's going to depend on the degree of the numerator and the denominator. So right, again, a rational function, we have f of x over g of x. Okay. If the degree of the numerator, so this one right here, is less than this one, it's going to be 0. We can see that pretty clearly. Let's say if we have like, sorry, that was a bad infinity. If we have infinity to the squared over infinity cubed, right, obviously this is going to grow to 0, right? We're going to skip the middle one, but if we go to here, right, if we had, say, infinity cubed over infinity squared, that would grow, obviously, towards infinity. But if they're equal, if we have infinity squared over infinity squared, this would be equal to 1. But if we have it equal to 5/3, it will be equal to 5/3. It all depends on the ratio of the leading coefficients. Why? Because these are just going to cancel. And any other terms that are in the top of this thing that are smaller, right, that are not part of the leading degree, are going to become negligible as we increase to infinity. So if you have a rational function here and the degrees are equal in the top and the bottom, eventually as x approaches infinity here, it's just going to become equal to the ratio of the leading coefficients. Let's take a look at some example questions here. Take a second, see if you can solve these. All right, the first one, we see the degree is 1 and the top degree is 1 on the bottom. We can use our rules. This will become 3/5. Next one, the degree on the bottom is larger than the degree on the top, so this is going to be 0. And the last one, this was going to be infinity because the degree on the top is larger than the degree on the bottom. Bang, 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 and we are done. Okay, in topic 1.16, we're working with a theorem called the intermediate value theorem. And this at first is going to sound very abstract and possibly very complicated, but once we go over the example, it's going to simplify everything for you, I promise. So, if there is a continuous function f of x on a closed interval ab, and k is any number in between f of a and f of b inclusive, there is an x value c on ab for which fc is equal to k. And that probably sounded like a lot of gibberish. We're going to take a look at this example, we're going to figure it out. So, let's say in this example, our a is 0. So this is a, and this is b, right? This here is b. Okay? This is going to be f of a, right? And this is going to be f of b. This makes sense, right? This makes sense. This function has to be continuous. It's on this closed interval. It's continuous over this closed interval, right? There's no gaps. There's no discontinuities. Okay. If k is any number in between here, so k is any y value from positive 1 all the way down, from positive 1 all the way down to negative 3, right? Then there is an x value c for which f of c is equal to k. And if you just use logic, right, basic logic here, this makes sense, okay? There has to be some value, right, some value here where k is represented, right? Because if we're going from here to here, then every single point within here to here has to exist. So let's say I wanted k to be equal to negative 1. Let's say k equals negative 1. Then at this point, whatever this x value is, this is equal to c, right? Because k is equal to negative 1 here. If I wanted k to be equal to negative 2, it could be here. If I want k to be 0, be here. Any point in between here, k is defined for. Okay, this works for any continuous function on a closed interval. And that is the intermediate value theorem.